Now let us look at the necessary and the sufficient conditions for maxima minima of functions of several variables. We know the necessary condition for the function of one variable, dy by dx equal to 0 and d2y by dx2 less than 0 for maxima and d2y by dx2 greater than 0 for minima. This is what we know, right? Now, we are going to look at the same thing for the functions of several variables using the concept of differentials, which we have done yesterday. Right, let me start by writing out in the differential form for the maximum minimum conditions for the function of one variable, and then I'll generalize it for more than one variable. Let's have a look at that. So for one variable function, let me repeat one thing again. I am doing only that much of maths here, which is required by me in my micro course, right? So this is not a complete thing. For complete lectures, I think the series, or at least complete basic lectures, the series which Vidhi is going to put up, that is going to be useful, right? For one variable function, z is equal to fx, like this. So you find out the differential dz equals to f dash x dx. This is what we have done yesterday, right? So dx is an arbitrary increment. Let's say that is not equal to 0. Let's say that is greater than 0. That's an increment. That's an increase. So it is greater than 0, let's say. So in case if f dash x equals to 0 is there, then dz is equal to 0. So note that. Dx is greater than 0. Is an arbitrary increment. Therefore, the condition f dash x equals to 0, right, implies dz equals to 0, right? Okay. Now d2z, if you want to find out the second order derivative, d2z would be f double dash x dx square. So dx square is positive. Dx square, that is the square of dx, that is positive. So the sign of d2z is going to be dependent upon the sign of f double dash x. So the sign of d2z is going to be dependent upon the sign of f double dash x, right? So when d2z is negative, that means when f double dash x is negative, then the stationary point which you are getting from this condition, from the first order condition, that is the point of maximum. Stationary point is the point of maximum, right? And when d2z is greater than 0, then stationary point is the point of minima. It is the point of minima. Fair enough. Okay. So what you can say is that the function z is equal to fx will have a maxima or minima if dz is greater than, if dz is equal to 0 and d2z is not equal to 0. So d2z could be positive, d2z could be negative. So all of this is just one variable. So I'm just repeating what we said earlier in the differential form. Thus, we can say that Z is equal to fx as maximum or minima if dz is equal to 0 and d2z is not equal to 0. If dz is equal to 0 and d2z is not equal to 0, now I'm going towards the function of several variables. That is, I'm going to pick up more than one variable in the function. Now, so let's say you have z is equal to fxy then. Z is equal to fx. So in that case, the differential, you have done this yesterday, is what? Del f by del x dx plus fy del f by del y dx. Fx could be written as del f by del x. Fy is nothing but the partial derivative of f with respect to y. That is del f by del y. So the change in z is going to come due to the change in x and the change in y. And you have to add these two changes in order to get the change in z. So dx and dy are the arbitrary increments. So assuming that they are non-zero, so dz is going to be 0 when fx and fy are 0, right? So note that. Dx and dy are the arbitrary increments let's say they are non-zero constants. So they are non-zero constants, then dz is going to be 0 when either del f by del x is 0, both del f by del x and del f by del y both are 0. Then only dz is going to be 0. So that is the first order condition. So that's a necessary condition for maxima or minima for the function of several variables, right? So that is the necessary condition. Or maxima or minima z is equal to fxy. What is the necessary condition? Either del f by del x is 0 or del f by del y is 0. Right? That means del z by del x and del z by del y are 0. So keep this thing in head. That is, how will you get the necessary condition for uh, for uh, for maxima or minima? Del z by del x is equal to 0 and del z by del y equals to 0 simultaneously. This is the point. For second order conditions, I mean, we won't be using much these second order conditions. We won't be checking them much, but just for the knowledge sake, you should know. So how much we will be using in our thing for solving the optimum problems, the second order conditions, but okay. It's like this for the second order condition. We have this thing dz equals to fx dx plus fy dy. Yeah. Let's just differentiate this. d2z is going to be dfx dx plus dfy dy, like this, right? I have told you yesterday also. You remember from yesterday's recording, I have told you these things. That when you find out the partial derivative of f with respect to x, it is not necessarily a function of x only. It can be the function of y also. So you need to differentiate this fx with respect to x and with respect to y. Right? So how is the partial derivative of x is changing? So partial derivative of x can change when x is changing and when y is changing. So you use the same thing, the way you have used it here. Right? So I'm not going to repeat that thing here. So I'm assuming that you have done the yesterday's recording. So if you have not done, please see how the thing which I'm writing is coming out here. Beta, वैसे the only thing is this. When you write fx as the function of x and y, then you find out, then you say this, del fx by del x plus del fy by del y dy, right? When you try to find out the derivative of the differential of the partial derivative of x, that is going to be this. So it is going to be this thing. So how is the partial derivative of x is changing with respect to x? So I can write this as fxx dx plus f, no, it's not y. It is x beta. Sorry, it should be x. Fxx dx plus fyy dy. And I have told you yesterday also that if you want to write how what is the total differential of the partial derivative of y, that is going to be what? Del fy by del x, sorry, del y del x, sorry. Del fy by del x dx plus del fy by del y dy, right? So this thing is fx y dx plus fyy dy. But due to Young's theorem, you can write fxy as fxx. Fxx dx plus, or sorry, fxy dx plus fyy d plus fxy dx, and even here I have written it wrong. It should be, yeah, it should be fxy. By dy. Right, and into dx. So when you write it, you get what? Fxx dx squared, right? Plus fxy dx dy plus fxy dx dy. So that is 2 fxy dx dy plus fy by dy. So this is d to z. This is d to z. Now we need to see when d to z is going to be positive and when d to z is going to be negative. Because when d to z is positive, that is the point of minima. When d to z is negative, that is the point of maximum. So I need to see that. We need to see that. So, because this looks very cumbersome, can I say fxx is a, dx is u, fxy is h, dx is u, dy is v, and fyy is b, dy is v. So I've just assumed these things. I mean, it is easy to write in a, u, b, h, this form instead of writing fxx, fxy. So I can write this as d to z au square plus 2h uv plus bv square. Now I have to use it in a proper way. Can I take a common and can I write this as u square plus 2h v into u whole upon a plus bv square. Now can I make this a complete square? Yes, I can. 2h upon a uv plus h square upon a square v square. So what I have done is I have just added and subtracted h square upon a v. This is what I have done. I've just added and subtracted h square upon a v, because this is, when you will open this up, this thing also become h square upon a v square. This thing is also going to become h square upon a v square. So when you open this up, this thing is going to be u plus h upon a v ka whole square plus, I can take v square common. This thing is going to become ab minus h square v square common upon a. So this is what we have got as d to z, right? But this is a square, so a into something positive, right? Okay, plus this term ab minus h square. We don't know whether it is positive or negative because ab can be greater than h square, ab could be less than h square, and we also don't know the sign of a, let's say, and this thing is positive. So we need to know the sign of d to z, because in case if d to z is positive, that is the point of minima. If d to z is negative, that is the point of maxima, right? We need to know, we need to form some cases. So let's look at first case. Case 1. If ab minus h square is positive, right, or ab is greater than h square. So this is given to you, that ab minus h square is positive. That is given to you. So everything is now dependent upon the sign of a. So this is positive. Then the sign of d to z will depend upon a. Then the sign of d to z will depend upon a, right? So if fxx, beta a kya hai? A is fxx. What is b? B is fyy. What is h? H is fxy. So I'm taking up first that case. If a is negative, a is negative means fxx is negative, and this thing is holding, ab minus h square is positive, that is fxx into fyy minus fxy ka square is positive, and fxx into fyy is greater than fxy ka square, And at the stationary point, d to z will be 0, will be less than 0. And the function fxy, or you can say z equals to fxy, has a maximum. Now, again, this condition is holding. AB minus h square is positive, but A is positive. This is the next case. If fxx is positive, and this condition is holding, so beta, everything is positive. Na? A is positive, this is positive, this is positive, everything is positive. So d to z is going to be positive. Is greater than f of x y ka square. Then at the stationary point, d to z is greater than 0. And the function z is equal to fxy has a minimum. And the function z is equal to fxy has a minimum. What could be the another case? Another case could be that this AB minus h square is negative. Then this is a saddle point. Is true. If AB minus h square is negative, right? That is AB is less than h square. That is fxx into fyy is less than f of xy plus square. Then the stationary point is a saddle point. The stationary point is a saddle point, and if AB minus h square is exactly equal to 0, then the criteria is going to fail. The point could be a point of maxima or a minima or a saddle point. So we don't know. Case 3. I'll be giving you a numerical example, so which will help you to see these conditions easily. Maybe in the next recording. This has already become very long. If AB minus h square is equal to 0, that is, if fxx into fyy is equal to f of xy square, then criteria fails. And stationary point can be a point of maxima, minima, or settle, right? So this is about your necessary and the sufficient conditions for function of more than one variable. For our purposes, I mean, we will be generally checking just the necessary condition and we will move on. Ideally, we should check, but not every time it is going to be positive. It is going to be possible. So remember that simultaneously, or these two partial derivatives, they have to be equal to 0. F of x equals to 0 and f of y equal to 0. You'll be using this a lot in this condition, at least, that del f by del x equal to 0 and del f by del y equal to 0 simultaneously. And I've told you the reasonings why they have to be simultaneously equal to 0. So in the next class, I'll give you some example of the necessary and the sufficient condition using a numerical example so that you understand it better, right? Thank you, Beta.